Hi, this is lecture 20 of the complexity class, and in this lecture we're going to prove something that we meant to prove a little while ago, which is Valiant's famous theorem that the permanent problem is sharp P complete. Okay, let's recall the permanent. So let A be a integer matrix n by n, and the permanent is given by this formula here. We sum over all the permutations of 1 through n of a kind of product of the generalized diagonal, the product of all the ai, comma, sigma I entries. Valiant's theorem is that computing the permanent, even on matrices that just have 0, 1 entries, which is equivalent to counting the number of perfect matchings in a bipartite graph, is sharp P complete. Okay, and to recall what that means, basically it means that there is a reduction from a canonical sharp P complete problem like sharp 3 set, counting the number of satisfying assignments to a 3CNF formula, to computing the permanent even on 0, 1 matrices. So that's what we're going to show in this lecture. And actually there's 4 steps in this reduction, 3 of which are pretty easy, and 1 of which is the main part. This is the part here that's highlighted in red is the main part. So let me tell you what these steps are. So we're going to actually reduce from sharp 3 sat to like a very slight variant, then reduce to the permanent on matrices with -1, 0, and 1 entries. And finally, we want to get to the permanent on 0, 1 entries. So the first reduction is one we actually saw before. We discussed in class in lecture 14, going from possibly negative entries to positive integer entries. There's actually 2 ways to do that. You can either do it via interpolation, using the fact that the permanent is a degree n polynomial. And that's a bit convenient because then it reduces the problem to permanent on matrices whose entries are just between 0 and n. Or you can do it a different way by going mod a very big number. And one downside of that is you get the reduction is to permanent of matrices with exponentially large entries, which is actually not so bad. It's still not a problem, but we'll stick with the interpolation version in our heads. And okay, after that, let me mention that this reduction here is quite trivial. I'll show you that, but it's almost nothing. This reduction here from permanent on general non-negative entries to permanent on 0, 1 entries, it's also going to be pretty easy. I mean, basically, there's going to be some graphs involved, and it's going to involve converting parallel edges to just single edges. So that part's not going to be too hard. So basically, all the steps here that were originally blue, I've drawn over them, but were originally blue are pretty easy. And this is the main step. So basically taking the sharp 3 sat problem on slightly balanced instances and reducing the problem of counting the number of satisfying assignments to computing the permanent of a matrix with entries -1, 0, and 1. Okay, so that's going to be the main reduction that we'll get to. And just to spell it out in slightly more detail, we're going to produce a polynomial time reduction that takes as input a 3CNF formula phi, let's say with m clauses, and with c satisfying assignments. And we're going to produce from it a matrix, A sub phi, whose permanent is simply exactly equal to basically c, but times this fixed constant. Okay, so it's not quite a parsimonious reduction, but it's almost parsimonious in the sense that it maps a formula with c satisfying assignments to a matrix whose permanent is basically c times some prefactor, which happens to be -2 to the power of 3m over 2. But the point is that this is like exactly known to the algorithm. Okay, so like once you get this, if you could compute this permanent exactly, then you would simply divide by this factor, and you would recover c, the number of satisfying assignments for your 3CNF formula. Okay, so that's what we're going to show, and it turns out that the permanent is maybe not the most convenient thing to work with. It'll just be nicer and easier to work with a much more graphical concept that's equivalent to the permanent, and that's the concept of cycle covers. Okay, so what is a cycle cover? Well, I'll illustrate it with a specific example. So let's say you have some matrix A of non-negative integers. Actually, they can be negative integers too. So let's say you have some matrix of integers, A. You're going to build from it a graph that has a number of vertices equal to the dimension of A. So in this case, 4. All right, so we think of the rows and columns as being indexed by vertices. And then it's just like an adjacency matrix of a directed graph. you put in an edge, a directed edge, whenever you have a non-zero entry. And furthermore, you label all the directed edges by their non-zero entry. You can also think about it if you want as like putting in the complete directed graph and also running zeros onto the edges sometimes. But it's more psychologically useful to just omit the edges that have a zero on them. Okay, so for example, because this entry here, 2, 3 is a 2, we have this edge going from 2 to 3, that's labeled by a 2. I should also mention that it's perfectly fine to have self-loops in the graph, sort of just by a coincidence. I chose a matrix where all the diagonal entries were 0. But for example, if this 0 were a -5, then that would mean you'd have a self-loop on 4 labeled by -5. Okay, that's possible too. It just doesn't happen to be the case in this example. Let me erase that hypothetical instance though. Okay, so recall that the permanent is given by this formula. And what does that translate to in terms of this graphical picture? Well, you see, first of all, we're summing in the permanent over all permutations, sigma. So I can draw a permutation like this. It's just a mapping from 1, 2, 3, 4 to 4 distinct numbers. And we think of this as like a mapping in the graph. And for each, so one thing is for each such permutation, we can sort of follow the edges that it corresponds to. So this is 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. So let's see, that's 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. Okay, and what you see is that you'll always start and end up in the same place, and you'll visit each vertex once. And in general, this was like a 4 cycle, but you'll not necessarily get a full cycle every time, but you'll get a collection of cycles. Now, looking back at the permanence formula again, like as we traverse this cycle in the permanent, you kind of multiply the matrix entries corresponding to the edge labels. Okay, so in the graphical picture, we're going to define the weight of one of these. It's going to be called the cycle cover, these traversals of the vertices, to be the product of the edge labels that you encounter as you go along. So for example, this one, if you remember, we went weight 1 and then weight 2. So weight 1, weight 2, and then we went 3 to 4, that's weight 1, and when we went 4 to 1, that's weight 1 again. Okay, so this particular permutation has, well, this product term equal to 2, and so in the graphical picture, we're going to say this is a permutation or a cycle cover of weight 2. Okay, so I'll give another example here. If we had this permutation 2, 1, 4, 3, so that's, let's see, 1 goes to 2, and then 2 goes back to 1. So that edge is not present. So, well, we can continue anyway. 3 goes to 4, and 4 goes to 3. You'll see, since that edge is not present, right, that means it has one of the terms is, or one of the weights is 0. So this whole weight for this permutation is 0. Okay, and so that's why it's nice to just not draw the 0 edges. What we think about is like, okay, if this does not correspond to a cycle cover that's actually present in the graph, then it's considered to be weight 0. Okay, let me give one more example. This is 1 goes to 4, that's here, and then 2 goes to 3, that's there, and 3 goes to 2, that's there, and 4 goes to 1, that's there. So luckily all these edges are present, and this one has weight, if you recall, 1 times 2 times 1 times 1, so that's a weight 2. And notice this is an example where it's not like a Hamiltonian cycle, it's a union of 2 cycles. Okay, so the permutations that are of non-zero weight are precisely, as I said, cycle covered in this graph. So these are unions of cycles that touch each vertex exactly once. And then we can reinterpret the permutation of, permanent of a matrix A as the sum of the weights of all the cycle covers in the associated directed graph. So I'll call that the total weight of cycle covers in the graph. Good, so just a few conventions here. It's very cluttered if you write in all the weights, and in our constructions, almost all the weights are going to be 1. So we'll have the convention that if I don't label an edge, it just means weight 1. So in this particular graph here, almost everything has weight 1, except for this one edge of weight 2. And okay, now we're going to get to studying cycle covers because, as we explained on the previous slide, the permutation of a matrix can be thought of as, I keep saying permutation, the permanent of a matrix can be thought of the total weight of cycle covers in the associated directed graph. So we're going to be doing reductions involving these cycle covers, and we'll have to develop a few little tricks. So let me start talking to you about tricks you can do with cycle covers. So trick number one, as you can see, is about replacing weights that are greater than 1 by parallel edges. Okay, so as I mentioned, it's quite convenient to have like these unweighted edges that stand for weight 1 edges, but we don't always have those. In this particular graph, we have this one edge of weight 2. And one thing I'd like to show you, and this is going to go into the final reduction to the permanent of 0, 1 matrices, is that you can get rid of positive weights that are greater than 1 integer weights by parallel edges. Now you might say, wait a minute, I mean, this is all supposed to correspond to the permanent of a matrix, and I understand how, if you have a n by n matrix, you can view its permanent is about the cycle cover weights in a n vertex graph, but, how do you incorporate parallel edges? Well, we'll get to that in a second, but just for now, let's imagine that in the cycle cover problem, parallel edges are allowed. Okay, so how do you get rid of a weight 2 edge? Well, you do the obvious thing. You replace it by 2 parallel edges. And in general, if you have a weight 3 edge, you can replace it by 3 parallel edges, and so forth. So what I want to claim to you is that this new graph with this weight 2 edge replaced by 2 parallel weight 1 edges has the same total weight of cycle covers. So this claim is easy, but it'll illustrate the kinds of claims that we'll be doing in this lecture, so let's go through it. So we have to ask ourselves, okay, now that we've replaced that weight 2 edge by 2 parallel edges, what are the cycle covers in the new graph? And there's a couple of kinds. The first kind is type 1 kind, is you could have an old cycle cover in the old graph that didn't even use that weight 2 edge. Okay, there's certainly cycle covers in the old graph that didn't use that weight 2 edge, like what's an example here? We can do, this one. 1 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes to 1. Okay, some jitter there. Okay, so that's a cycle cover in the old graph that didn't even use that weight 2 edge. And of course, the cycle cover is still present in the new graph, and its weight didn't change, so everything is fine with those guys. Okay, now in the new graph, there are also, you can also get cycle covers from old cycle covers that did use the replaced edge. So perhaps we had this cycle cover before, like 1 goes to 2, and then previously it was like 2 goes to 3 on this weight 2 edge. And then maybe 3 goes to 4, and then 4 goes to 1. So that was a weight 2 cycle cover. And what happens with that? Well, for each of those old cycle covers, we can turn it into one of 2 different cycle covers in the new graph. We can either replace that 2, 3 edge with this edge, or we can replace it with this edge. Okay, and so these new cycle covers have half the weight of the previous one, but there's 2 of them. So therefore, they add up to the same amount in the end. And you can see that if you had, a weighted edge of weight 3 and you replace it with 3 parallel edges, then, you would get 3 new cycle covers, each of weight 1, instead of 1 cycle cover of weight 3. Okay, so that's maybe not too unexpected, and that shows you that you can get rid of these weights that are exceeding 1 with parallel edges. Now let's return to this question of are parallel edges even allowed? And, well, formally speaking, they're not in the permanent problem. But, with another little reduction, you can get around that. So this will be trick number 2 with cycles. And trick number 2 with cycle covers is that whenever you have any edge at all, and this trick doesn't fundamentally have anything to do with parallel edges or anything, it's just a very generic trick. Whenever you have any edge at all, you can subdivide it by sticking in a self loop in the middle. Okay, so I did it, in this particular edge that we created with from the weight 2 edge, but you can also do it here. If you want, you can just randomly take this, edge, let's say from 3 to 1, and stick in a new vertex here, and put a self loop on it. And the point is that this operation does not change the total cycle cover weight at all. Okay, so you can randomly stick in these vertices with self loops in the middle of edges, and it doesn't change anything. And that's useful for solving this parallel edges problem, because you see, here we have this parallel edges between 2 and 3, and we fundamentally fixed it by, subdividing this 2 to 3 edge here with vertex 5. We could have also subdivided this one, or both of them, whichever, for fun, doesn't matter. But just subdividing one of them will do the trick. Okay, so let me convince you of this claim. And the proof is similar to before. I mean, again, we have to ask ourselves, okay, in the new graph with this extra self-loop vertex 5 added, what are the cycle covers? And again, we could have had some, if you think about it, like every cycle cover in the new graph, it could come from like an old cycle cover which didn't even use that edge. So perhaps, see if I can draw this one. And in that case, this is not a cycle cover in the new graph because 5 is not covered by any cycle, but then you can just take the self-loop, and that has weight 1. So whatever the weight of this old cycle cover was, and in this particular example, all the cycle covers have weight 1 because I don't have any weighted edges anymore. But anyway, whatever it was, even if it had weights, we just multiply it by 1 in this cycle cover. And so we have the same cycle cover of the same weight. Okay, type 2, well, in the new graph, you have some cycle covers that kind of come from old cycle covers that did use the subdivided edge. Like this is an old cycle cover, 1 goes to 2, 2 goes to 3 along this subdivided edge, and then say 3 goes to 4, and 4 goes to 1. Yeah, whatever weight this previously had, it has the same weight. Actually, I suppose here we need, let's say if, I didn't mention this, but if like the old weight, it's not a big deal when all the weights are 1, but if the old weight was like 7, then maybe you should make, this one have weight 7, and this one have weight 1, and this one have weight 1. The point is that, when you had a cycle cover in the old graph that did use this subdivided edge, you have a corresponding new one that just takes the length 2 path and doesn't take this self-loop. Great. Okay, so that's another basic trick with cycle covers. We're kind of getting the basic tricks out of the way here. And because the existence of this trick which we'll actually use in multiple ways, but one of the uses of this trick is to show that, parallel edges are perfectly fine. Okay, so henceforth we're going to allow ourselves parallel edges, and we won't use this trick. We won't draw the trick, at least. Okay, so in fact, at this point, what we know is enough for us to finish this little reduction. Whenever you have a weighted cycle cover kind of instance, where the weights are between, let's say, 0 actually, and polynomial in n, as is the case at this stage in the overall reduction, you can get rid of these weights or convert them to all 0, 1 weights, which is our goal, with a polynomial in n size blow up. Just take every weight that's bigger than 1, convert it to parallel edges, subdivide those edges, and you'll get an instance with the same total cycle cover weight, or a bigger matrix with 0, 1 entries with the same permanent as the older matrix. Good. Let me actually mention that this is not the most efficient way, actually, to get rid of large weights. It's the easiest way, but it's not actually the most efficient way. And as a little exercise for you, you can show that you can actually get rid of weights that are even exponentially large, meaning weights that can be written down with polynomially many bits, still with poly n size blowup. Okay, so in fact, if we go back to this slide, it means that actually just the whole general permanent problem with non-negative entries, where you are paying for the full input size, in particular potentially writing down exponentially large numbers, even that can be efficiently reduced to permanent of 0, 1 matrices. And I'll just give you some hints for it. Let's say you're trying to get rid of a directed edge in your instance with weight 256. Well, consider this graph with path of length 8 and edges of weight 2. So you can see if everything goes to plan, this will be a good way to simulate weights that are large powers of 2. And then if things are not powers of 2, but maybe they're sums of powers of 2, well, this is a further hint. If you have an edge with weight 256 plus 32, or whatever that is, Consider this graph with parallel edges. Okay, so I'm sure if you put those all together, you'll be able to complete this exercise, which is a good exercise to know. The general permanent for non-negative integer matrices can be also reduced to 0, 1 permanent. Okay, so actually at this point we're basically done with like little tricks to do with the cycle covers. We're almost ready to like get on with it, get on with the real reduction. But while we're here and while this picture of this interesting graph is still on the screen, let me say something about this. I call this graph the NAND graph. And I didn't put up here just for jokes. It turns out that this graph is a key gadget in the sharp p-completeness result we'll see. And what is the key property of this little 4-vertex graph? It's the following. It's concerned with cycle covers vis-a-vis like which of these outside edges they may or may not take. Okay, so look at these 3 outside edges I've highlighted here in red. Form this like outer circle. I know it's a little bit weird because there's also this inside edge here which is parallel to it, but ignore that one. I want to focus on these 3 outside edges. Okay, so it turns out that if you take all 3 of these edges, you cannot get a cycle cover in this graph. And that's pretty clear. If you try to take all these 3 edges, there's like no way for you to, get a cycle passing through 4. Okay, so you cannot take all 3 outside edges. But it turns out that for every way of taking fewer than 3 outside edges, so if you take 2 or 1 or 0 of these outside edges, you can get exactly 1 cycle cover. So I'll show that on the next slide, but let me give you one example. Let's say you decide I only want to take this edge from 1 to 2, and I don't want to take this outside 2 to 3, and I don't want to take this outside 3 to 1. Well, there's exactly one way to finish it to a cycle cover, and can we figure out what that is? Yes. You have to take this inside 2 to 3 edge, and then 3 to 4, and then 4 to 1. Okay, that's the unique completion to a cycle cover. And perhaps you can see that that's going to be a useful kind of gadget for 3CNFs, because the OR of 3 literals is the same as the NAND of the negation of those literals. I'll let you think about that for a second. And so this gadget somehow is enforcing that like you cannot have all 3 outside edges, but anything else is fine. So here's the little picture. You can hit pause on this video and study it if you want, but it shows for all the 7 possibilities of taking a non-full subset of the 3 outside edges, how you can pick sort of the inner edges to complete it to a cycle cover in a unique way. All right. Great. Whoops. Okay, so let's see, we've done this part, and there's one more trivial step in the reduction to go before we get to the main business, and it's already popped up on the slide here. I think I did things in slightly out of order. Okay, what is this sharp 3-sat with a superscript balance problem? Very tiny twist on sharp 3-sat. It's just the sharp 3-sat problem with this special property that every variable in your 3CNF, I've got some bug here with the pen, every variable in your 3CNF appears equally many times unnegated and negated. Okay, so I've just given a typical 3CNF. It doesn't have to be that every variable appears the same number of times negated and unnegated, but it's very trivial to like achieve this with a polynomial time parsimonious reduction. And the trick, which has been up on the screen for a little while now, is simple. It's just an observation like consider this clause, xi or not xi. Well, this is always satisfied, so you can add it to any 3CNF you want, and it doesn't change the number of satisfying assignments. It doesn't destroy any satisfying assignments because it's always satisfied, but it doesn't gain any either. So you can freely add a clause that looks like this to your 3CNF without changing the number of satisfying assignments. And notice, of course, that it has one more occurrence of xi positively than it has occurrence of xi negatively. And so if your overall input 3CNF is like deficient in positive occurrences of xi, then just add a bunch of copies of this thing. And similarly, if you're given a 3CNF instance with an overall deficiency of negative appearances of xi, then just add a bunch of copies of this clause until you have the same number of positive and negative xi's. And you can do this for all the the variables to get into this balanced state, so that you have a 3CNF formula where every variable appears equally often, unnegated, and negated. Okay, and it doesn't change the number of satisfying assignments. Great, so this is this trivial reduction that we'll have at the beginning. And actually at this point we've done all the trivial pieces of the reduction. So we eventually wanted a reduction from sharp 3 sat all the way to the permanent of 0, 1 matrices. It starts out by this little reduction to get to the balanced version of sharp 3 sat. The main piece is coming up. It reduces the permanent of -1, 0, 1 matrices, or more accurately, or equivalently I should say, computing the total cycle cover weight of directed graphs with weights that are -1, 0, and 1. And then these last two little hops are easy. We can do this one by the interpolation trick, or by computing mod a really big number. And then we can get rid of these positive weights and move them down to 0, 1 by this edge duplication trickery. Great. So that's done. And let me just say what property we really use out of this sharp 3 sat balance thing. It's that every assignment, no matter what, no matter if it's satisfying, if it's unsatisfying, it doesn't matter. Every assignment makes exactly half the literals false and half the literals true. And here, when I say that, I don't mean like among the n literals. I mean among the occurrences of literals in the 3CNF formula. Okay, so your 3CNF formula, you know, it has like, you know, x1 or x3 bar or x5 and x1 or x7 running out of space here, or x10 bar. Oops. Yeah, here I mean we have two occurrences of the positive literal x1. Okay, and this is really the key property that we're going to use when you're in sharp 3 sat balanced. If your 3CNF has exactly m clauses, then for every assignment at all, we get 3m/2 false literals occurring in the formula itself, and 3m/2 true literals occurring in the CNF itself. Okay, so I'll fade that out. And yeah, now we're going to come to the main reduction. So things are actually going to start now, in some sense. So what is overall going to happen in this main reduction? We're going to take a balanced 3CNF formula phi with m clauses and some unknown c, a number of satisfying assignments. And in polynomial time, we're going to reduce it to, well, a matrix, A sub phi, whose permanent is exactly equal to this quantity, -2 to the power of 3m/2 times c. Okay, and that's good, because then if you can compute the permanent of this matrix, you can divide by this known quantity and get back c. Good. Well, of course, as I said, we're going to work these cycle covers, so we'll actually reduce to a weighted digraph with weights -1, 0, and 1, such that the total cycle cover weight is exactly this quantity. And, oops. Right. So in fact, this is the thing that we're going to prove. This is kind of quite key. This is the final property of our reduction. Our weighted digraph is going to have the property that for every satisfying assignment to phi, which makes p literals false and q literals true, there'll be cycle covers in the weighted digraph of total weight this amount, -1 to the p times 2 to the q. And that'll be the key property we prove. And it's because, you know, these factors, -1 and 2, are different, that we actually have this little balance trick. So if we didn't have this balance trick, we'd be in a little bit of trouble, because, like, different satisfying assignments would potentially give us cycle covers of different weights. But you see, oops, let me tell you that in a second. You see, this property is crucial, that every assignment, actually it doesn't matter if it's satisfying or not, every assignment makes the same number of literals in the formula true and the same number of literals false. Okay, and that's convenient because, and that number is 3m/2, because then for every satisfying assignment, this total weight will be this factor, -2 to the 3m/2. Okay, so now let me put that little observation back up. This is a bit of a twist because we're actually not quite done. Well, the story on the digraph we reduced to is not quite done being told. The point is it's going to have a bunch of cycle covers that somehow correspond to satisfying assignments for the 3CNF phi, but it's actually going to have a bunch more cycle covers, but all of these cycle covers that are somehow not properly encoding a satisfying assignment will have weight that eventually sums up to 0. Their total weight will be 0. Okay, and this is kind of like the, maybe the coolest trick that you can do that. So the fact that with these spurious cycle covers that we don't actually like, because they don't correspond to what we want in the gadget construction, actual assignments, their total weight is 0. So it doesn't mess up this fact that the ones that correspond to real assignments have some exact known cycle cover weight. And getting this to happen, this total weight to be 0, is sort of where we crucially use, our ability to use negative weights in the digraph. Okay. So, in some sense, finished clearing my throat, and we're now ready to literally do the main reduction from balanced version of sharp 3CNF counting to this cycle covers and weighted graphs with weights -1, 0, and 1. And I should say that at this point, really, it's not that different from a super classic undergraduate textbook reduction from 3-sat to, I don't know, something like Hamiltonian cycle. Okay, so we have to take a 3-sat instance and produce some kind of digraph from it, and there'll be some mildly complicated gadget, but it's actually not too insane. You'll see it's not so bad. And, that's how it goes. Well, but now we're going to do it. We're going to actually literally see these gadgets. Actually, there's only a small number of gadgets. Okay, so as is kind of typical, we'll devote little pieces of the graph called gadgets to the variables and also to the clauses in our input 3CNF phi. So we have some phi here with variables x1 through xn, and we're going to have a bit of digraph for each variable, and it's just going to look like this. For each variable, xi, we're going to have 2 vertices and 3 edges, and they're all unweighted edges, edges of weight 1. And 2 of them kind of go from left to right, and 1 of them goes back. And before I look at these labels that I've written here, let's just observe what are the cycle covers in this tiny graph. Well, you have to cover both vertices, and you have to take this back edge. There's no way to get around that. But you have a choice of how to go forward. Okay, so the 2 cycle covers in this graph, in other words, are sort of going along the top and coming back, or you can go along the bottom and come back. Okay, so you have 2 choices, and we're going to use those 2 choices to encode an assignment. Okay, so we think of going along the top and coming back as supposed to be encoding that xi is set to 0, and going along the bottom and coming back is supposed to be encoding that xi is set to 1. Okay, so we plunk down n of those, 1 for each vertex. Sorry, 1 for each variable. Okay, I said that. And now we have a gadget for each clause, also as typical in these gadgety reductions. So, if you have m clauses, we're going to have m of these gadgets. So a gadget for a clause looks at the clause, and it's a clause as a disjunction of 3 literals. So maybe it's x5 or x7 bar, or really got to look into this pen bug, x8 bar. Okay, so in this case, li is x5, lj is x7 bar, lk is x8 bar. And right, so as I mentioned before, the OR of 3 literals is the same as the NAND of the 3 literals negations, right? To say that one of li, lj, or lk is true is to say that it's not the case that all of them are false. Okay, good. So we think of these as, I guess, NANDs on the negations of the literals. And so therefore, our clause gadget is this graph that I mentioned before, this little 4-vertex graph, this NAND graph. Okay, and as we sort of intimated before, and now we have explicitly, we kind of, for each clause, we introduce this gadget, and we label these 3 key outside edges by, I guess, the negations of the literals. So again, if this clause gadget was for x1 or x2 or x3 bar, then we'd sort of label this guy with x1 bar, and label this guy with x2 bar, and we label this one with x3. Okay, and so now, for example, if here I was 2 and this was, x2 equals 0, and this was x1, 2 equals 1, we're going to somehow try to like attach or relate these edges to this edge. Okay, but I'm getting ahead of myself a little bit. Let's take another quick look at this clause gadget. Good, so we label these outside edges by the negations of the literals in the clause. Let me actually mention one slight other thing about this diagram. Just to reduce clutter, I put these like double-sided arrows in. So really this is just a less cluttered way to draw both arrows. So that really actually happens here and here and here and here. But going forward, I'm going to draw them in this less cluttered way. Okay. And right, so just to remember, the key property of this clause gadget is for all the 3 outside edges, which we now think of being as labeled by these literals, if you take all 3, then you can't get a cycle cover. And if you take any subset, you can get exactly 1 cycle cover. So in fact, if you think about the graph at this stage, where we've just put in like all the variable gadgets and all the clause gadgets, what's going on? So far, everything is totally unweighted, so it's enough to count just like the number of cycle covers. Okay, and how do you have a cycle cover in this graph so far with this many disjoint pieces? Well, you take a cycle cover in each vertex piece, so that corresponds to making a variable choice, an assignment choice for each variable, xi equals 0 or xi equals 1. And you also sort of commit to some way to satisfy each clause. So I mean, to get cycle cover in clause gadget, you have to take some subset of the outside edges, perhaps these 2, and then finish it to a complete cycle cover. And sort of that's like committing to say, oh, I'm going to satisfy this clause by making literal li false and literal lk false. So that's all well and good. There's just one problem, which is that there's like no connection between your encoded variable assignment and your encoded clause assignments. Okay, so now the only remaining task is to just enforce consistency between your variable assignment and your supposed way of satisfying all the clauses. So in some sense, what we kind of wish to do is identify 2 edges in this graph. Okay, so again, let's say like I is 2 and down here, and let's say this one is standing for x2 bar, perhaps. Okay, so to say that x2 bar is true is to say that x2, let me draw a 2 in here, is 0. So we would somehow, in this case, like to somehow identify this edge with this edge. If we could do that, then like everything would be kind of consistent. I guess by identify, I'll say this in the next slide, but like somehow enforce that in every cycle cover, like if you take this edge, then you also have to take this edge. And conversely, if you don't take this top edge, then you're not supposed to take this top edge. Okay, so you just want to make all your clause assignments exactly consistent with your variable assignments. Okay, so let's make a tiny definition here. We'll say that 2 edges in your digraph are perfectly identified if your overall graph has the following property. Whenever you have a cycle cover in the overall graph, it contains E if and only if it contains E prime. So every cycle cover has the property that you take either both E and E prime, or you take neither E and E prime, of E and E prime. Okay, and if we can somehow arrange for that in our graph, we'll say that the edges E and E prime have been perfectly identified. And if we had the ability, as we're going to see, we don't quite have this ability, but if we had the ability to like just arbitrarily perfectly identify pairs of edges, we would be exactly done. Okay, because we would just do the exact thing we were talking about on this slide. We just for every vertex gadget, we'd take its assignment whenever it appeared in a clause. Sorry, we take its associated edge whenever it appeared in some clause. We'd somehow like identify these 2 edges. And that would be great because then every cycle cover in the graph, overall graph, if we could do all these identifications, would exactly correspond to a satisfying assignment. Because, in order for it to be a cycle cover within this graph, it has to take not all of the outside edges and therefore satisfy the clause. And, it'd be, for every cycle cover, every choice of, assignments up here that you can complete to a cycle cover in all the clause gadgets would be a satisfying assignment, and everything would be hunky-dory. Actually, there's a little bit of a wrinkle here. I'm about to start telling you the punchline of how we can't perfectly identify edges, but we can put in some kind of gadget that effectively does the job. But again, I have to stop for a little wrinkle that's at the level of these, cycle cover tricks we talked about at the very beginning, trick 1 and trick 2. So let me take a little time out for this wrinkle, which is that every variable actually appears in multiple clauses. So there are many appearances of, x7, both positively and negatively, in the list of all the clauses. And so, our dream scenario would identify the two x7 edges appropriately with all of their appearances in all the clauses. And then we're in a bit of a funny situation where we're identifying one edge with multiple other edges. And when I eventually get to the gadget that helps us identify edges, it's really designed to identify just pairs of edges, like one edge with another edge, okay? And it's not designed to identify one edge with multiple other edges, okay? So this little wrinkle, we're gonna fix that issue, and then finally we'll be able to talk about trying to identify edges. So the idea for fixing this little wrinkle is trick 2. If you recall trick 2, it's the ability to subdivide an edge without changing anything at all. So if we want to identify this edge, one of these kinds of edges, with multiple edges, which we do, we're just gonna, if we want to identify it with 10 edges in clause graphs, because there's 10 appearances of this variable or its negation, we'll just subdivide all of these edges by that self-loop trick 10 times. Okay, so this is the trick we saw before. If you have any old edge at all, if you stick a vertex in the middle of the edge and put a self-loop on it, then it doesn't change the total cycle cover weight at all. Nothing changes. But it has a slightly bonus extra feature also that we're going to use, which I'll mention now. So here's the picture for subdividing edges. This giant thing with the blue and the green is an example of this little variable gadget where I subdivided each of the xi equals 0 and xi equals 1 edges 1, 2, 3, 4, 5 times. I guess I now have 5 edges for each of them, just by doing this trick of sticking a self-loop vertex multiple times in the middle. Okay, so I'm going to do that. This is what I would do if, let's say, variable xi occurred 5 times, positively and negatively, in the clauses. Actually, I guess every variable occurs 3m over 2n times positively and 3m over 2n times negatively, because we're starting with balance sharp-sat. So in fact, we exactly know how many times we need to subdivide each edge. And here's the actual bonus twist, which is that I claim that all of these xi equals 0 edges, these 5 xi equals 0 edges, have the property that they're perfectly identified according to our definition. In other words, if you have a cycle cover in this graph that has this gadget in it now, any such cycle cover, if it takes any one of these edges, it has to take all of them. And otherwise it takes none of them. And you see that's true. If you take one of these edges, you have to have a cycle cover. So if you take this one, you have to escape from this guy, so you have to take this one, and you have to take this one, and you have to take this one, and something has to be coming into this guy, so you have to take this one. And that's it. And then, you're forced to take this one to come back, and you don't take any of these. Okay, so similarly for the xi equals 1 edges. So what I'm saying here is that this little subdivision trick, took our gadget that looked like this, and it just made an arbitrary number, 5 number of copies of this edge, and identified them all together, which is sort of exactly what we want. Okay, so basically now we freely have as many copies as we wish of these variable edges. And that's great. So now the wrinkle is fixed. You know, every time you have a variable clause occurrence, you know, we can assign each one of these to a variable clause occurrence, like a combination of a variable and a clause. And now we can just worry about identifying pairs of edges, okay? Because these guys are all identified with each other. So, you know, if xi appears in this clause, then we can try to identify these two edges. And if it appears in some other clause, we can try to identify these two. And, you know, if it's appearing in exactly 5 clauses, then we're perfectly good to go. Okay, so that's the end of that wrinkle. And now we're finally, you know, come to the good stuff, or, you know, the last piece of the puzzle. The last thing we sort of have to implement, or at least try to implement, is the ability to identify an arbitrary pair of edges in our graph. Okay, so let's, you know, forget about all the other gadgets for now, and like imagine that we have some weighted digraph, some total weight of cycle covers, and we kind of want to get into the situation where, like over here, the only valid cycle covers either take both of these two edges or neither of these two edges. Okay, that's what we need to do if we were to try to perfectly identify this pair of edges. And I'm sorry to say that we will not in general be able to perfectly identify them. But we'll see a gadget that does something that's good enough. So more precisely, what is going to happen? So this is the old graph over here. And we have these two edges we want to identify. We're going to build from it a new graph. So we're going to transform it to something that looks like this. So there's going to be some gadget, which we'll see soon, that we somehow plunk down between these 4 vertices. And here, this is the key thing. This is the property that this gadget is going to have. So property are A, B, and C. So property A, for every old cycle cover in the old graph of some weight W that takes both of these edges, so whenever you have a cycle cover in the old graph that happens to use both of these edges, which is a good scenario for us. We like when, like, the edges, these two edges are either both taken or both not taken. There's going to be a corresponding new cycle cover in this new graph that, you know, does some stuff like this, and it'll have a total weight of the negative of the cycle cover weight over here. So if you had some cycle cover taking both edges over here of weight W, then there'll be a new corresponding cycle cover in the new graph of weight minus W. Okay, and it's not so important that it's like -1 times W, it's just important that it's like some simple function of W. Okay, property B is similar. It's like whenever you have a cycle cover in the old graph that takes neither of the two edges that we're trying to identify, so we don't take these guys and we don't take this guy, then there's going to be some corresponding cycle covers in the new graph that somehow like don't involve really passing through the gadget, although there'll be some edges within the gadget. There'll be some corresponding cycle covers in the new graph whose total weight is 2W. Okay, and again, it's not so important that it's literally 2W, it's just important that it's like some clear function of W. And finally, there's property C, which is the following. Once you plug down this gadget, there are actually many cycle covers in the new graph. And some of these cycle covers in this new graph, as you'll see, like correspond to old cycle covers, either that take both edges or that take neither edge in the old graph. But there'll also just be like some other cycle covers in this new graph with this new gadget that like either feel like they're corresponding to old cycle covers that take only one of the edges but not the other, or the cycle covers in this new graph will just like have nothing to do, like it'll just not have anything to do with the old graph at all. But, you know, property C is this: all these remaining cycle covers in like the new graph, the ones that are not associated to nice old cycle covers, have total weight 0. Okay, and so they just all add up to nothing. They get canceled out. Okay, so that's what I'm going to show you, and now let's see how that sort of finishes the proof of the whole reduction. So we have this whole reduction here. We have the variable gadgets, which we can subdivide if we want. We have the clause gadgets, and we just need to like identify a bunch of pairs of edges. And, you know, we said that if we could perfectly identify some edges. Let's see. If we could perfectly identify some edges between the variable gadgets and the clause gadgets, then everything would be great. Then we'd have the property that the number of satisfying assignments for our 3CNF instance would be exactly equal to the total weight of the cycle covers. In fact, just equal to the number of cycle covers. But we cannot perfectly identify edges. We just have this identification gadget, but we can stick it in instead. So these are the three properties of it, A, B, and C. And okay, so finally, what happens if we do that? You see, then when we have this sort of weak identification maneuver that has these three properties, what happens? Okay, for every satisfying assignment of phi, we kind of get a cycle cover in the old graph where the identification condition is satisfied, like the cycle cover, like for every edge that we try to identify, like this edge and this edge, it either takes both of them or neither of them. And as we saw from like these properties, we get associated cycle covers in the post-identified graph of a certain weight. So basically, every time we, sort of glue two edges together in the correct way in the new graph, every time we have a cycle cover in the new graph, which corresponds to gluing two edges together in the correct way, we pick up a factor of either -1 or 2. So you should think about doing these identification gadgets, these attempts at identification, one at a time. Okay, and every time you take a good cycle cover in the old graph, it corresponds in the new graph, it's sort of stands in bijection in the new graph with some cycle covers whose total weight goes up by some factor, or gets multiplied by some factor, which is either -1 or 2. Okay, and so if you propagate this for all the identified edges, you get the property that for every satisfying assignment in phi, we finally, after identifying all the edges, get a total cycle cover weight that's equal to, basically -1 to the power of the number of times you sort of used both edges in your good cycle cover, times 2 to the power of times, to the number of times you used neither edge. Okay, now let's think about this for a second. When you use both edges in your old cycle cover, it's because you're implicitly setting the associated literal occurrence, the negation of the literal, to true. In other words, you're setting the literal to false. So really, it's every time you have, in the good case where you're doing things properly and setting according to a satisfying assignment, every time you have a false literal occurrence, that's when you're taking both edges, and particularly taking this edge and therefore picking up a factor of -1. And every time you have a true variable occurrence, that's when you're not taking one of these outside edges, and that's when you pick up the factor of 2. Okay, so good. So overall, for every time you have a satisfying assignment of phi, then finally after you attempt to identify all the edges and you sort of do it, you get new cycle covers in the new final graph of total weight equal to this. And that's why we start from sharp 3-set balanced. It's because it makes these two exponents exactly the same. And so we don't get a different amount of cycle cover weight for each satisfying assignment. It's for every satisfying assignment, we get the same known amount of cycle cover weight. And by the way, if you have an assignment that doesn't satisfy the 3CNF, then it just cannot be completed to a cycle cover in the final reduced graph. That was the property of our NAND gadget. Okay, so this is exactly, this identification gadget completes the reduction, because if you remember this slide from a long time ago, this is what we finally claimed we were going to achieve. For every satisfying assignment that makes some p literal appearances false and q literal appearances true, we get total cycle cover weight equal to this amount. And luckily, since we have the balanced sharp 3 set, P and Q are always the same. In fact, it doesn't matter if the assignment is satisfying or not. You're always going to have 3 over m over 2 false literals, 3 over 2 true literals. So the final total cycle cover weight is this known factor minus 2 to the power of 3m over 2 times the number of satisfying assignments. Great. So you can put the video on pause here for a second and think about that a little bit more if you like. The final piece of the lecture is to just show you this identification gadget and show you that it has these 3 identification gadget properties, A, B, and C. Okay, so here is the plan, and here's what we have to prove about it up here. And now I'm going to reveal what's in this gadget here. And it's actually quite simple looking. I mean, the analysis of it is a little bit tricky, but the gadget itself is very simple. It looks like this. There's 3 vertices, and most of the edges are unweighted, but like, you know, this is a little bit of a key. There's one vertex with a self loop with weight -1 instead of +1. And also, as you note here, I've, to reduce clutter, drawn some bidirected edges, but really this stands for one edge that looks like this and one edge that looks like this. All right, so that's it. That's the whole method by which we try to identify 2 directed edges in the old graph. We stick in a copy of this gadget. Okay, so now we're going to heroically do the analysis of this gadget. So what do we need to do? We need to study all the cycle covers that are in the new graph. And the way to study them is to divide into cases by asking yourself, for every cycle cover in the new graph, which of these 4 edges here does it use? It could use none of them, it could use all of them, it could use some subset of them, and we have to like literally look at all 16 cases, although some of these cases are kind of simple because they cannot happen. But this is how we're going to do the analysis. Okie dokie, so let me just show you like one case. So one case is we're like studying cycle covers in this big graph, and we consider all the cycle covers that take this edge here, and this edge here, and they do not take this edge, and they do not take this edge. So what can such cycle covers look like? I'll show you on the next slide, but let me just draw something here. So let's consider U. On one hand, we've already decided that, you know, every vertex has one incoming edge and one outgoing edge in a cycle cover. So we've already decided its outgoing edge is going to be this. So its incoming edge has to be like some, you know, other edge that's in the part of the graph that we've not shown. And by the way, this edge also exists in the old graph. Okay, so a particular cycle cover that's using these top 2 edges, but not the bottom edges, you know, has to come into U from the outside. It goes in this way. And actually it has to, I mean, this vertex, its out edge has already been chosen to be this one, so it goes into V. And then the cycle continue must continue externally to V. This, by the way, exists back here. On the other hand, we have decided down here that for U prime, we're not taking this outgoing edge, which means that in the cycle cover that we're analyzing, it has to use some external outgoing edge, which also exists back here. Of course, you also need some incoming edge. Okay, that's fine. And, oops, this should have said V prime. That's going to be a mistake on all the slides henceforth. Well, you can deal with it. U, V, U prime, V prime. Good. So, in the new graph, right, where was I? Okay, so yeah, V prime. You see, we decided that it did not take this incoming edge, so it must have used some incoming edge from the grander outside graph, and also an outgoing edge from the rest of the world. And again, these edges must also be here. Okay, so this cycle cover that we're, you know, theoretically analyzing here, which uses these top edges but not the bottom edges, it's in good shape, except it's not done because it has not covered these vertices. Okay, so let me erase some of this ink. Yeah, what this is showing, I'll still circle these guys. Right, this is showing that if you decide to take these 2 edges, you have to be coming in from here, going out here, going like this, going like this. As I said, all these edges exist in the previous graph. And what I'm saying is actually, you know, if you take this supposed cycle cover from the new graph, over here. It uses these top two edges, but not these bottom two edges. And it, successfully covers all the other vertices. That cycle cover must exist. We could take all the exact same edges in the old graph, and also this edge, and we get a valid cycle cover in the old graph. Okay, so for every cycle cover in the new graph that uses these top two edges, but not the bottom two edges, there's a corresponding cycle cover in the old graph. Now, notice in the old graph, it's one of the cycle covers that we don't like. We don't like these cases. We're trying to identify UV and U prime V prime. We don't like the cycle covers that take the top edge, but not the bottom edge. But it's going to be kind of cool. So let's say this was some inconsistent cycle cover. I put inconsistent in quotes, just meaning that you have some old cycle cover that takes the top edge but not the bottom edge. These are the kinds we don't like because we're trying to identify these two edges. Let's say you have such a cycle cover and it's of weight W. Then you get a corresponding cycle cover or you can get corresponding cycle cover in the new graph. But as I said, we're not quite finished here because there's still two vertices that we have not covered yet. And one of the ways to finish the job is to take the two self loops. And if you do that, the product of these edge weights is -1 and 1. So if we multiply that against all the other edge weights from out here, we finally get a cycle cover in the new graph of weight -W. We took all the edges out here that had total weight W. This edge weight was 1, so that meant all the external edges multiplied to W. Okay, so all these external edges multiplied to W. This one multiplies, this one's 1, this one's 1, this one's 1, but this one is -1. Okay, so finally we got a cycle cover over here of weight -W. That's one possibility. The other possibility to finish this cycle cover is to take both of these directed edges, which really are two directed edges that look like this. They both have weight +1, so this gives us a cycle cover of weight +W, and ta-da! The point is that these two cycle covers cancel each other out. Okay, so what I'm saying here is there are some cycle covers on the new graph that take these edges, but not these edges. And all of these cycle covers, their total weight eventually cancels to 0 because they correspond to they have an exact correspondence to cycle covers in the old graph that took the top edge but not the bottom edge. And whatever the total weight, W of all these cycle covers were in the old graph, you get cycle covers in the new graph of total weight -W, and you also get some more of total weight +W, and those sum up to 0. So, hooray. This phenomenon will occur for all of the bad cases in the new graph. Okay, this is exactly, case 1 is like an example of what we want to happen, where there's some bad cycle covers that we wish didn't exist. They do exist, but luckily, if you sum up all their weights, it gives 0. Okay, so for example, we just did the case where we took the two top edges over here and not the two bottom edges. There's, a totally symmetric case where you take the two bottom edges, but not the two top edges. Okay, so that's another case that is also done because all those cycle covers exist, but they add up to 0. Let's do another bad case. Let's do a case where we're studying all the cycle covers in the new graph that use this edge, and they don't use this edge, and they don't use this edge. So what's going on with all these cycle covers? Again, I want to argue that all the cycle covers in the new graph that, make these 4 choices like this, there are some cycle covers like that, but their total weight is going to be 0. Okay, so what must the rest of the cycle cover in the new graph look like? Well, again, we've decided we're going to have this edge, so that means we have to have some incoming edge here. And we've decided, for example, that we're not going to have this edge, so V's incoming edge doesn't come from the inside of the gadget, so it must be coming externally and going out externally. Down here, we are taking this incoming edge to, again, this is supposed to be V prime. So it's going to have some external coming edge, but no external incoming edge. And U prime, we decided we're not taking this vertex, so we're going to have the cycle cover looking like this vis-a-vis the rest of the graph. Okay, Now, okay, that's what I've just drawn here. Oh, I had my arrows pointing in different directions than the slide arrow, so it looks a little confusing. So let's get rid of that. Good. Now, these guys, we're not going to argue about them by arguing about cycle covers in the old graph, because actually, you know, these cycle covers in the new graph don't correspond to anything over in the old graph. Because, I mean, I don't know, you cannot have cycle covers in the old graph that look like this externally, because it's just, it's impossible. But don't have to worry about it. We'll just worry only in the new graph for this case. So let's say we've decided on these choices so far, and the weight so far is W. So like all these outside edges in this cycle cover that we're analyzing, that takes this edge, but not these two. Let's say all the weights so far multiplied to W. Okay, now this cycle cover is not finished. There's two ways to finish it. So one way is drawn here. You can take this edge and you can take this self loop, and that covers everything that extends you to a valid cycle cover. And that finish has total weight negative W, because you took a factor of 1 here and a factor of -1 here. And there's a different finish. I mean, you can instead go like this and go like this. Take two weight 1 edges, and that finish has total weight plus W. Okay, great, those cancel out. Fantastic. So all the cycle covers in the new graph that, you know, fall into this case, you take the top left edge, the bottom right edge, but not these two edges. Cycle covers like that exist, potentially, but their total weight is 0. Great, so we've knocked off some bad cases. There's potentially a few more bad cases, but they're going to be not so hard. So here's another bad case. Let's say your cycle cover takes this edge, this edge, this edge, but not this edge. Now, what do the remaining cycle covers, or what does the rest of the cycle cover in this graph look like? Well, it looks non-existent. It's impossible. You cannot have a cycle cover in this new graph that takes, you know, this edge, this edge, this edge, but not this edge. And why is that? Well, I don't know, like this vertex here has to have some incoming edge. It's not this one, because you've already used up this guy's outgoing edge. So maybe it's coming from this one, but then this guy needs some incoming edge too, and it can't be this one because you know, this guy's used up his outgoing edge. Okay, so I mean, if you just stare at this for 2 seconds, you see there's no way to complete this choice of the edges to a cycle cover in the whole graph. Great, so the total weight of cycle covers that, you know, make these 4 choices is 0, because no cycle covers like that exist at all. Okay, so in fact, all the bad cases are now complete. Like all the bad cases that we're going to end up not liking contribute 0 total cycle cover weight. And really, there's only going to be 2 good cases that are left. The 2 good cases that are left are when the cycle cover in the new graph takes all 4 edges, and the case where it takes none of the edges. Okay, so we've actually completed part C of the identification gadget properties, and we have to check part A and part B. Okay, so as I said, there's 2 good cases to check, and one of the good cases is that all 4 edges are taken. Once again, we always ask ourselves, what must the rest of the cycle cover in the new graph look like? And it must look like this. So since we've definitely taken all 4 edges, the external connections are that we have like an incoming edge externally from U, outgoing one from V, an outgoing one from V prime, incoming one to U prime. And by the way, all these edges exist in the old graph. And in particular, we can count all the cycle covers in the new graph that use all 4 edges by associating them with cycle covers in the old graph. So you see, once you've taken all this external stuff in the new graph, there's corresponding external stuff in the old graph, and you can complete it to a cycle cover in the old graph by just taking both of these edges, the 2 that we're trying to identify. Okay, so there are potentially many cycle covers like this in the new and the old graph, but whenever you have a cycle cover like this in the old graph with some weight W, that's exactly, we can associate it to cycle covers in the new graph. Okay, and in fact, if you look at the new graph, there's only one way to finish this to a cycle cover in the new graph. Like everything is covered except for this pink vertex. The only thing you can do is take the self loop. Okay, and so the only finish has total weight minus W. Okay, and so for every cycle cover in the old graph that takes both these edges we're trying to identify, you get a corresponding cycle cover in the new graph whose weight is the negative of the total weight in the old graph. Great, so that's what we just said. That's gadget property A. We're almost done. We just got to do gadget property B, which is slightly more tricky, but not really. Okay, this is the final good case where none of the 4 edges is taken. So again, we ask ourselves, all right, what must the rest of the cycle cover in the new graph look like? Since we don't take any of the incoming edges for V or V prime or the outgoing edges for U or U prime, those must be coming externally from the graph, from the rest of the new graph, so it looks like this. And for every external set of choices in the new graph, we have corresponding external choices in the old graph, and that corresponds to like a cycle cover in the old graph, so that's good. So there might be many cycle covers like that, but for each one in the old graph where neither edge that we're trying to identify is taken, it has some weight W, and so that completion exists in the new graph. And now again, we finally just have to sort of count up what are all the ways to complete this to a cycle cover in the new graph. And really, as long as it adds up to anything that's not 0, we're in good shape. It's going to add up to 2. So in fact, there are 6 ways to finish this picture to a complete cycle cover. So I guess I'll just see if I can quickly identify them. So you can take all of the self loops. That gives you -1 total weight multiplicatively. Let's see, you can take, there's another way to get -1. Let's see, oh, you can take, right, you can take the self loop here, that's -1, and you can basically take both parts of this bidirected edge. So you can do that. That gives us another -1. And now there's going to be a bunch of ways to get a +1. So let's see. Right, you can take both these bidirected edges, that's 1, 1, and this self loop, that's a +1. You can do the reverse, you can take both of these, and this self loop, that's 1, 1, 1, that gives us another +1. And let's see, oh, you can go in a little loop like this, that's 3 + 1 edges, and you can go the other way. Which way did I just go? You go this way. That's another +1. Okay, so I just did the exercise for you. There's 6 finishes here, and these numbers add up to +2. Okay, so for every cycle cover over here in the old graph that doesn't use either edge, that uses neither edge, you get some cycle cover completion. These cycle cover completions exist in the new graph, and for each one of them, there's like 6 ways to fully extend it to a cycle cover. And if the old one had total weight W, the new ones will have total weight +2 times W. And that's gadget property B. And we did A and we did C. So ta-da, we've verified all the gadget properties. And believe it or not, we are now done. The whole reduction is complete. And we've shown Valiant's theorem that computing the permanent, even of 0, 1 matrices, is sharp P complete.